Hello, I'm Jungi Kim, working as a CTO in LevelUp. I'm going to talk about the next generation SQLAlchemy with native asyncio support, including several technical issues I have experienced before and during the migration. I have faced all the issues in this talk with the Backend AI project, which is the flagship product of LevelUp. So first, I'm going to introduce myself. This is my GitHub profile page. I'm working with open sources daily, including contribution to C Python and managing both personal and company projects. For instance, Python 3.10 will include my addition of context-lib.a closing API to clean up async generators using async context managers. I have presented multiple talks in PyCon Korea. For example, the one in AR tools in PyCon Korea 2017 and Callosum in PyCon Korea 2018. So both of these are libraries actively used in the Backend.ai project here. So the Backend.ai project is a very big async IO-based product with more than 20 paying business customers now by providing a streamlined interface for container-based GPU computing clusters. Through this Backend.ai project, I could accumulate a decent amount of good and bad experiences on Python async IO, and this talk is also the extension of that. So this talk is organized as follows. I will first introduce the basic core and ORM APIs of SQLAlchemy briefly, and a series of database adapters in the existing async IO ecosystem. Then cover the technical issues faced and resolved in the Backend.ai project while using AIOPG before migration and SQLAlchemy in general. And I will show some highlights of the new SQLAlchemy version 1.4 updates and describe technical issues I have faced afterwards during the migration. I believe that most of Python developers would have heard of SQLAlchemy, even though they don't have actual programming experience with it. It is a kind of de facto standard database library in Python with a highly flexible ORM API. On ORM, or Object Relational Mapper, is a general scheme to make individual objects in the host language to reflect individual database records in SQL in a bidirectional way. SQLAlchemy also provides a DB API abstraction so that it can be used with multiple different databases with the same API, but also with database-specific extensions as dialects. So let's first see how the SQLAlchemy's core API looks like. It's almost a set of Python classes and methods that have one-to-one correspondence to the SQL equivalents. The query composition API starts with a select, insert, update, delete statements instances, and you can append additional SQL clauses such as where, order by, group by, and etc. by method training. The ORM API maps the class objects with the database records, and these objects can be manipulated in a Pythonic way. For example, you may instantiate an object and set its attributes just like plain Python objects, and then apply it to the database using the sessions commit method. There are actually many more details to cover in ORM though, such as making foreign key relationships and joint queries, but I'm not going into such gory details in this talk. One of the problems with SQLAlchemy in the async IO ecosystem was that most asynchronous bindings do not support ORMs. SQLAlchemy's core API has an explicit timing of making contacts with the database server, namely query.execute method. So it is relatively easy to support asyncio adaptation by replacing or extending the connection object. ORMs, however, often use implicit commits for updates and the default field fetches. So this makes it difficult for library developers to replace the underlying query server system to run as fully asynchronous functions. Of course, there are other approaches using the Green Dot ecosystem or completely new ORM implementations, but I'm not going to cover those here. So I'm going to show some API examples in the previously available synchronous SQLAlchemy APIs. So the first one is ARPG and ARPG.sa. So most async database bindings have provided a new engine and connection and transaction implementation that accepts the SQLAlchemy's query objects in their execute methods. So here you can see the SQLAlchemy constructed SQL statements which is passed to the library specific engine and connection and transaction objects. So here is the example of async PG. So it's more or less same with just minor naming differences. Note that AIOPG is an asyncio wrapper on top of the well-known PsychoPG2 library, while async-PG is a brand new native implementation of the PostgreSQL client protocol using Python, reaching the performance of fetching millions of the rows in 1 second. It is developed by the same group who developed the UV loop, which also provides a faster async IO event loop implementation. So here is another case, the databases library. Yes, the name is databases. It's a generic async wrapper for multiple different databases, such as MySQL, PostgreSQL, and SQLite. It directly accepts both the SQL statements as strings and the SQLAlchemy's core query objects. So here you see the most of the code parts are just the same, with just minor differences in the connection and transaction APIs. So in backend.ai, we could not use ORMs at all because everything is async. Though we kept using SQLAlchemy in favor of schema management and custom type serialization for complex type columns, such as JSON or my own custom defined column types. In the early versions of backend.ai, we tried async PG for more performance and async PG SA as our SQLAlchemy adapter. But due to some custom column type conversion issues, which was not resolved for quite a long time, I migrated to AIOPG because it had a more stable and consistent behavior on the type conversion of SQL columns. So what were the other technical issues we have faced at that time? So AIOPG itself was quite mature, but it has lost most of the project motivations because it was expected that SQLAlchemy was going to implement its own async support sooner or later. So there were several critical edge case bugs which was not fixed for a very long time, for example, like 1.5 years, due to limited development resources. So I got hit by some cases and I had to make workarounds because database related bugs are often revealed in production, not during development. So for one example, canceling in the middle of a enter method of a transaction block, the connection itself is not released back to the connection pool even its operation was canceled. So this actually caused the denial of service issue when the client side network, like Wi-Fi, like a packed room, connections are unstable. And in such situations, the API handlers got canceled because the HTTP connection drops at random timing, and thus the database connections and transaction blocks are canceled at random times. And another issue with ARPG is that it does not run on Windows, while SQLAlchemy runs well on Windows. So still, we don't officially support the Windows environment in backend.ai, but we have a future plan to run it natively on Windows. So asyncio uses a special event loop called the proactor event loop on Windows to utilize the IO completion pulse API, which provides high performance and consistent API across many different waiting handles and sockets and so on. So in Linux, everything is universally abstracted as file descriptors, but this is not true in Windows, as we see in the IO completion pulse API. So the proactor event loop has several missing APIs, such as add reader or remove reader, which deals with the file descriptors in Linux. But ARPG relies on these APIs to implement asynchronous wake-ups with existing Cyclepage2 socket connections. And we have used Alembic for schema version management. Generally, it is a great companion to SQLAlchemy, considering the nature of continuously evolving software. However, there are also a few tricky cases you need to take care when using it. The first one is to add or remove enum constants as a part of migration. Depending on the database engine you are using, it may be just a simple replacement of existing text columns, but in PostgreSQL, you need to redeclare the internal enum type because the PostgreSQL engine uses its own internal constant mapping table. So this may make the migration scripts to be quite complicated because you need to convert the column to the text first and perform string-based replacements before converting it back to the new column enum type, while also removing and re-adding the enum column type definition. So yeah, and the second one is a more subtle one. Most Alembic migration scripts usually just add or remove columns, but sometimes you need to make queries to refer existing column values to compose the values of new columns. In such cases, you often go to import the table definition by importing the existing source code, but this is actually very dangerous. So let me elaborate why this is a kind of concerned case. So importing the table definition from the current source code may make the mismatches of the table definition in the migration and the source code, because the source code always represents the latest version of the table schema, but the migration scripts need the exact version when the migration is applied to. So, for example, if you manage the source code in Git, the Git's like main branch has always the latest version of database schema in the source code, like models, submodule or subpackage. But if you import it directly from the migration script, then the migration script will use kind of the wrong version of table definition. So this actually can make very hard to find bugs, because usually developers, when the developers write migration scripts, the source code is also in that specific table schema version. But so the test passes and the CI passes, everything looks good. But if you happen to do some database maintenance jobs after a long time, after many updates of the source codes, then you eventually find the mismatch of these table schemas. So this is actually what I have experienced. So after then, I revisited all migration scripts I have and copy and pasted the exact table definitions from the exact commits from for each migrations. Well, here is another technical challenge we have faced with the SQLAlchemy. So I have several like a JSON database columns to represent kind of semi-structured data. For example, the schedulers, update status, or like containers, reason to terminate, and so on. And I wanted to incrementally update such a JSON column in the database level without fetching the column in prior. So for example, when you increment a single integer column in the database, you don't have to actually get the value by the select statement to the Python and increment the variable in Python and then update it. You can just refer the existing column in the SQL statement, SQL update statement. But for simple kind of scalar columns like JSON, integer or strings, it is a very simple task. But for like a complex types like JSON columns, you need a special dialect functions like SQLAlchemy's JSONB build object or something others to concatenate and coalesce the empty values to replace it with default values and so on. So this is a quite kind of cumbersome code to write down every time. So I made a special function that generates SQLAlchemy column expression to incrementally update on existing JSON columns. So yeah, I think we could improve this core in more general way, but this is what I did at the time. So yeah, I think this would be a good kind of tip for you. So finally, we got the SQLAlchemy version 1.4 in this March. So the SQLAlchemy team has released a version in this March and with many new feature additions, saying it's the most extensive release in at least 10 years. Yeah, this is a very, very big update, including all the like native async support and time annotation support for the next future version, and universal and transparent SQL compilation cache, and so on. Yeah, all these looks very good, but actually, yes, like living with the bleeding edge is quite painful task. So there have been more than 24 patch releases since this March, with many bug fixes with the new async backend caching and transaction handling. The SQLAlchemy Core developers did a great job, but I also had to struggle with those issues until they were fixed. Yeah, so far. SQLAlchemy 1.4 has a very big meaning in their roadmap. So it's a big stepping stone towards its 2.0 release. All codes must be updated to work with 1.4 before migrating to 2.0. And 1.4 introduces a forward compatibility mode with the future flag when creating engine instances, which will become the default behavior in 2.0. So how does it support asyncio natively? First, it uses the async PG library as the connector backend, which is great in terms of performance. It provides async native engine connection and transaction objects like the existing async adapter libraries do. The execute method fetches all result records at once asynchronously, while stream method yields the records as the server sends, which may be required to handle a large number of record sets to prevent memory pressure. So existing adapters have provided usually only one style. So having both styles in the official SQLAlchemy APIs is a good design, I think. So yeah, you can use execute here, then you will get the result at once in this await statement. But if you use a stream like here, then the results will fetch it through the async iteration. And SQLAlchemy also provides a special method called runSync to wrap and run existing synchronous query functions asynchronously, effectively bundling multiple SQLAlchemy API calls into a single awaitable using a greennet. So when you install SQLAlchemy 1.4 with asyncio support, you also need to install greennet by side. This allows us to reuse SQLAlchemy's kind of managed schema creation codes instead of emitting raw SQL statements as I shown in the prior slides. So this runSync function is very powerful, so that it makes the bridge between the old legacy SQLAlchemy codes to incrementally upgrade to the native asyncio codes. Now the ORM also got the complete revamp to support asyncio support asyncio. So all ORM calls are now required to use session context managers explicitly. So every code here has a session, is wrapped with a session. And this makes it to be explicit, the timing of commits or rollbacks in the async context. And the official documentation recommends two extra options to avoid implicit IOs happening without explicit await statements. So the first one is eager defaults in the database table definition class. So this is to ensure the eager resolving of columns default values like here before async evaluation and refresh, so that asynchronous attribute access does not make implicit asynchronous API calls. And the second one is expire on commit option on the session factory. And this is by default true, but you recommend to set it first so that implicit fetch not to occur when accessing attributes after commit, just like the default values here. So the three major methods when you make like actual database access with asynchronous ORM is that commit here, commit or rollback or refresh. These are the three major explicit point of asynchronous access to the database. And you may wrap the legacy functions with the runSync function as shown in the previous slide. So so there are actually many technical issues during the SQLAlchemy 1.4 migration in backend.ai, but I'm just going to skim over that because actually most were in the bugs of the early releases. For example, so it took almost 3 months to get stabilized enough to deploy on actual customer sites. So the problem for me was that sometimes it was difficult to distinguish whether the root to source of the problem is the library's bug or my mistakes, especially when it comes to connection and transaction management issues. For example, there are a few more critical issues like swallowing of cancellation errors, which is a very critical issue in asyncio ecosystem, as I mentioned in PyCon Korea 2019 presentation. Also, using runSync API for levels or non-async SQL APIs requires installation of greennet. So this is usually automatically installed by the extra requirements dependency table in the package, but it seems that you may need to specify the dependency manually, depending on some platforms such as non-x86 architectures. I think this is a small bug in the SQLAlchemy, but I think it will be fixed soon. So finally, I'm going to describe the most complicated issue I have faced after initial migration. So backend.ai's sessions go through a few predefined states from pending to running by the scheduling process. So you can think that a session is composed of one or more containers. So when backend.ai used ALPG, we had to stabilize the transactions for all these state transitions of the backend.ai session life cycles with read committed isolation level using automated load test that spawns and interacts with hundreds of sessions concurrently. After migrating to SQLAlchemy 1.4, everything just began to break up. Oops. So we tracked down the issue and found that there was a big difference in the connection and transaction management in ALPG and SQLAlchemy. So we employed multiple solutions to make things to work correctly again. First, we raised the isolation level to serializable, which is the highest level supported by PostgreSQL. In this mode, all transactions are kind of critical sections. But as you may think now, it does not scale well. So PostgreSQL offers additional options to the transactions. For example, read-only transactions and differable transactions. In most cases, it runs these like read-only transactions run in parallel, assuming that read-only transactions are dominant compared to normal like writing transactions. And we adopted PostgreSQL's auto-visual lock to make the scheduler to run exclusively in only one manager process when there are multiple manager processes on multiple nodes, because a single iteration of scheduler execution involves multiple split transactions. And we also need to properly retry the mutation involving transactions if there are serialization failures to ensure the update. You cannot just ignore serialization failure errors because the scheduler must continue on. Yeah. So the problem is that there is no way to rerun context managers in the standard Python syntax. So I had to wrap all non-read-only transactions as a function with carefully split code boundaries, not to repeat the Python size state mutations twice or multiple times. So one thing you need to take care is the SQLAlchemy's DB API error, just wraps all underlying database error codes. So you need to manually pinpoint the exact error code to react with the specific errors, like a serialization failure. For example, PostgreSQL, asyncio PG returns the database side exit code in PG code attribute, and you need to check it the value by referring the database manual. Yeah. The last thing we are doing for the SQLAlchemy 1.4 migration, yes, it's not finished yet. So it's the adoption of the ORM. So currently we have lots of boilerplate codes to convert SQLAlchemy raw object into typed attribute classes or data classes like here. So it will be actually also a big journey to the complete migration. And there is another big topic related to GraphQL integration. So I think these are another major topic to cover in maybe other opportunities. So after resolving the transaction synchronization issues, I got several thoughts. Intrinsically, is RDMMs a good solution for strongly consistent state synchronization in distributed systems like backend.ai? So probably it's okay to use like a hard serialization of transactions for small or medium scale systems, just like our customers, but it may become a big bottleneck for cloud scale systems. Maybe we need to go back to Redis or migrate to etcd to ensure better consistency with better performance and scalability, while while keeping structured data in the SQL database. Or maybe another option is to adopt cloud vendor provided scalable databases like Google Spanner or something others. Yeah. Also, as I mentioned, the synchronization, the transaction synchronization issue was kind of hidden under the hood when we used ARPG. So there are many technical differences in the connection pool implementation and transaction management in ARPG and SQLAlchemy. And I believe that the symptoms were better exposed because async PG's performance was far better than ARPG and making it easier to get race conditions. So I think, yeah, this is kind of the result of good engineering in the library side, and it exposed more fragile surfaces of hidden in my program. So here is the summary. Now, SQLAlchemy, the Python's de facto standard database library, has a new version 1.4 with many new features, including asyncio native ORMs and the core APIs. It's based on the high-performance async PG library, so asyncio applications will benefit from it. SQLAlchemy developers did a great job, but living on the bleeding edge is, as a user, is still painful. I think now for you guys, it's a good time to try out SQLAlchemy 1.4 in your applications, as most big issues were resolved in the first 3 months after this March. The migration in backend AI let us realize that we had actually many hidden bugs, synchronization issues related to session lifecycle management. RDMS may not be the best solution for implementing such a strong consistency, but it's better to have explicit chances to test and analyze state management schemes when you write your own applications. Database transaction isolation levels may not guarantee what you expect from the database. So read the database manuals carefully and please be unsure, get it tested. So here is a bonus slide. So yeah, replacing the database engine of a live product. Yeah, the backend AI is already being used by several big enterprises and institutes. So and we just did this a SQLAlchemy v1.4 migration with just one update. And yeah, so we had experienced many issues hidden under the cover, and yeah, it was a very difficult job. So it's just most likely similar to building an airplane while it's flying. So yeah, that's the life of a startup as well. So this is pretty much of the end of my talk. So thank you for listening and watching this video. Yeah, thank you.